All right, so the purpose of this video is to look at how to draw a slope field and use that to represent a differential equation. And a differential equation is merely just an equation that happens to have a derivative in it. And we've kind of been doing differential equations a little bit throughout the year, but this really will formalize that. And the second half of our chapter really focuses on solving those. So here's our first differential equation. And again, I know it's a differential equation because there's a derivative, right? dy dx. So there's definitely a derivative, and it's an equation. There's an equal sign. And then notice you also have some other variables that aren't derivatives. And so the first thing it says is draw a slope field to represent this differential equation at these lattice points. And the lattice points are just the integer points, so like 0, 0, 1, 1, 1, 2, negative 1, 3, right? All the points that are defined by integers. That's what it means to be a lattice point. And what we're going to do is we're just going to represent the slope at those lattice points, based on this equation. So, like for example, the point here, 0, 0. So the point is 0, 0, right? It's the x value that I'm interested in. And so if I would put 0 into the x, 2 times 0 is 0. So I know that the slope at that instant would have been 0. And so what I'm going to do is I'm going to, I guess I'll pick orange. I'm going to draw a slope of just a segment that has a slope of 0 to represent, that's what the behavior of the tangent line would have been at that instant. And then if I go over here to 1, 0, the x value is 1. So the slope, 2 times 1, would have a slope of 2. So that's a little bit kind of like a steeper line like that. And then this point here is 2, 0. Its x value is 2. So 2 times 2 is 4. So it'd have even a steeper slope. And then at 3, 3 times 2 is 6. So it'd have even a steeper slope, right? So I'm just trying to draw a little segment that would represent that tangent line if there would have been a curve there. Now, the fact that it's only depending on x, right? Our derivative is just 2x. So that means like when all of the x's have the same value, regardless of their y's, in this case, they'd have the same slope. So the point 0, 1, 0, 2, 0, 3 all have an x component of 0. And 2 times 0 would be 0. So I can kind of be efficient in drawing in these slope values because I know that at every instant, those x components are 0. And similarly, if I think about like what's happening in this particular column, right? All of those points have an x value equal to 1. And so 1 times 2 is 2. So I would be able to match sort of that slope. Match that slope grade. And again, it's just kind of like my sketch of what I think a slope of 2 is. It doesn't have to be perfect. But then when I go out to here, because all of those values have 2 as their components, it should be a little bit steeper because 2 times 2 is 4. So, trying to make them parallel the best you can. And then this should be 6. And it just happens that this particular differential equation is only dependent on the x. Some of them depend on the x and the y, which we'll see. Now, let's go to this column here, which is all negative 1. 2 times negative 1 would be a slope of negative 2. So they all have the same slope of negative 2. And then you can see the next pattern, right, would be negative 4. So a little bit steeper in the negative direction. And then the final one is negative 6. So even steeper. And again, it's just a sketch. Now, on the AP exam, you won't have to do this many. Usually they narrow it down to just like maybe a quadrant. But there's our slope field. So at every lattice point, we know the slope of the tangent line. And in my head, I kind of stand away from it and look at it. It kind of gives some motion to this differential, kind of gives it some shape. And so then it says, well, why does it have this shape? I hope you see that it is sort of sort of quadratic in nature, right? Like if you think about the trend of these lines, we're trying to pick a color, I guess, doesn't really matter. It's sort of, in this shape, right? This parabola shape, that quadratic shape. And the question is why? Well, think about that. We know a lot about calculus. If your differential equation is 2x, you could work backwards. Someone's function who could it be that has that derivative? Oh, your function could have been x squared plus some constant. And so this really illustrates a whole family of functions that would satisfy that differential equation. And as soon as you know something about the graph, you could actually solve for C. And that's what it talks about for finding the particular solution. All of a sudden it says, hey, negative 2, 1 is part of my graph. So if you know that negative 2, 1, you could even plot that point like negative 2, 1 right here, then all of a sudden you can draw a parabola that might go through that particular solution. And then algebraically, we could solve. If we know this is our differential equation antiderivative, we could say, well, 1 is equal to negative 2 squared plus C. So 1 equals 4 plus C. Therefore, C should have been a constant negative 3. So then my actual particular solution would have been x squared minus 3. So I was a little bit off on my graph up here. So like going through negative 3. So I know at this point, and then 1, 2, this point. So then I'd want to actually draw, make it a little bit thicker. Here would be my particular solution. Okay, and that's it. A differential equation gives us a visualization of what the derivative is behaving like. So now the next example, you don't have to necessarily watch me do all of the lattice points. You could do them and then fast forward. But the idea is that you're only looking at where y is positive. So again, on the AP exam, this might be a little bit closer to what you would be expected to do. It's less points. And this one just happens to be dependent on y. So if I think about along the x-axis, all those y values are 0. So I know that this would be a 0, and this would be a 0, and this would be a 0, and this is right, 0, 0, 0, 0. And then, if at the next set of lattice points, all of these have a y value of 1. So slope of 1, slope of 1, slope of 1. And again, it's all based on what your differential equation is. And then this one would have a slope of 2, so a little bit steeper. And, again, it's not perfect. That's okay. And then up here, slope of 3. So as long as you can kind of see a trend that the higher I go, the steeper I am on these. And so it sort of looks, like that there's like maybe a horizontal asymptote at 0. Because it's flattened, and you kind of get this motion of kind of coming down, maybe like that. I don't know. That's kind of what I see. So then it says find a particular solution that contains a point 5, 1. So I want to actually solve this differential equation. Well, the thing is that if I say dy dx is equal to y, I have to make sure that I put the y variable with the derivative of y. And I, in the other example, like y was already in terms of x, so it's okay. So for this, what I want to think about is moving this y value over so that it's with the dy, and moving the dx over so it's kind of separated, and that's what's called separation of variables. So I'm going to think about that y as like y over 1, and almost like just like I said, like move this dx over. So now dy is equal to y times dx, but then move the y under, so it's like 1 over y dy is equal to just like nothing's left over, just a 1 dx. Okay, so now when I solve this, I'm going to introduce the integral sign. So I'm going to integrate both sides. And the fact that I separated the y variable to dy, and then even though it's a constant, we'll call it the x variable with the dx. Now I can integrate both sides and not have to worry about any kind of unknown chain rule or things that would have happened in my derivative. So what's the antiderivative of 1 over y? It's natural log of y. Now it'll be a plus c, but there'll also be a plus c on the other side. So that, when I could just put them together, it's just 1 plus c. Antiderivative of 1 would just be x, so then plus c. And, it says, the particular solution contains the points when x is 5, the y value is 1. So I could think about, all right, so when x is 5, the y value is 1. And that actually works out really nice because what's the natural log of 1? 0. So I know my constant has to be -5. So now I can take this equation and say, oh, natural log of y is equal to x minus 5. But a lot of times, a lot of times we want to solve this explicitly for y, if possible. So how do I solve this for y? Well, I can raise both sides to the e, like e is the base, like e to the, as what I like to call it. We're going to e to the both sides. So we'll go ahead and do e to this side and e to that side, and e to the natural log of y is going to cancel. We're just going to get a y value, and we can really ignore the absolute value of y for two reasons. One, it tells us y is positive, but also two, because all of a sudden now we have this exponential function, which is already positive, right? E to the x, actually e to the x normally looks like this, right? But then if we shift it to the right 5 units, it's still going to be like that. So there's our particular solution that goes through the points 5, 1. And go back and in hindsight, take a look. That really looks like an exponential function, right? So that, to me, that's awesome. I know 5, 1's like way over here, so we have this function that goes something like that. Now, the other thing I want you to take a look at in hindsight is look at your equation. It says pick a function whose derivative is equal to the function, right? This is what that says. The derivative equals what you started with. The derivative of y is y. Well, the only function that's true where it's not a trivial function is e to the x. So that was kind of cool in my head. I'm like, oh yeah, that sort of makes sense. Okay, so here's what I'm going to ask you to do. I'm going to ask you to fill out example 3 on your own, and then I'll have one short, quick video where I'll start with it's already filled out, and then we'll do the next example. Because, again, you don't need to listen and hear me think through all of these slope values. You evaluate it at each particular point. Okay.